The last hour I embarked on an attempt to persuade you that water has structure. And I'd like to continue that this morning because it bears on our, thank you, our description of sediment beds, and particularly on their erodibility. Just a quick review. 1888, Rowland proposed that there was structure in water because of the negative expansion coefficient as the temperature rose to 4 degrees centigrade. Water contracts as the temperature rises to 4 degrees centigrade. That was a rather perceptive conclusion. At that time, there wasn't complete agreement on the existence of molecules and atoms. So the idea that there was some kind of structure in there was really an advance for the time. Not during the subsequent years, there were quite a lot of structures proposed, like dimers and trimers and rings, 5-membered rings and 4-membered rings and various kinds of structures, but it was all speculation. Until 1933, Morgan and Warren proposed a mixture theory, and the basis for their proposal had to do with X-ray diffraction. What they did was to send a beam of X-rays through a little stream of water, a falling stream of water, and X-rays were scattered by the atoms and molecules actually largely by the oxygen atoms in the water stream, so that if you looked at the density of the X-ray scattering as distance along this surface, actually the camera was a cylindrical camera with film around the edge, and the distribution of X-rays was determined by the density of the darkening of the film. And if you plot that as, we'll call this angle theta here, as theta, what they found in intensity here, what they found was that there was at low temperatures, there was a distribution something like that. There's actually broad peaks. Now in crystals, where there's long-range order, there are very sharp peaks. And I might digress just a minute to explain that. If you consider atoms in a crystal having a long-range order, I won't specify any particular structure, but consider them as layers, then there's some angle theta that this beam will this is 2 theta. 2 theta. Some angle theta at which the scattering by atoms in this layer, which will also be theta, will be reinforced by scattering in this layer. That is, when the angle is just right for a given wavelength, lambda, the waves coming from this atom will be in phase with waves coming from the atoms in the adjacent layer, so that you get reinforcement of the scattered beam. Whereas at other angles, the waves are not in phase, so that you'll get cancellation or partial cancellation. We call this D. From that geometry, you can calculate that n lambda equals 2d sine theta. This is called Bragg's law. So that having this kind of a distribution, some kind of peaks, indicates that there must be at least some kind of order in the water structure, in the water molecules. they're broad because obviously there's a lot of thermal motion. It's not firmly fixed like crystals in a structure. They calculated what's called a radial distribution function. I'll show you some in just a few minutes. That indicated that there are 4.4 atoms, molecules, around nearest neighbors, I'll call it. On the average, that there are 4.4 on the average nearest neighbors to each atom. I won't go into the computation of radial distribution functions, but the idea is...
I'm sorry, what is N? Is it an integer?
N-O. N, you can see that you could have any number of spaces like this, and if they reinforced, you could have it. So N, and also you can have the lambda N wavelengths from here being reinforced by, or I should say N lengths, wavelengths from here being reinforced by this one. So it's not, it doesn't discriminate let's see, how should I say it? You can have multiple layers and get the same signal as you can from a single layer. And in actuality, as the angle changes, it becomes less strong, so that you usually don't have trouble picking out number 1 for n equal 1. Well, they calculated that each molecule has about 4.4 nearest neighbors, and they proposed that the water structure was a mixture of tridymite-like, that is like a silicate mineral, clusters in free molecules. That is, it's a mixture of molecules, free molecules, and some kind of a crystal-like structure. And this plot, they thought, was due to the fraction of it that's crystalline in the in the water. Let me show you some radial distribution functions. These are actually from neutron diffraction instead of X-rays, but they're the same distribution. Can you all see that? This is distance in angstroms, and each of these are separate curves, where this is 1 on the curve, and this line would go right through the mean of that curve. You can see there's a peak at about 2.8 plus. It's 2.84 is actually where it is. A peak, and then there's a secondary peak. This would be the second most distant atoms from the near atom, and there looks like something, maybe something further on. This is at well, let's just look at the water. This is deuterium oxide, heavy water, and this is regular water, 4 degrees centigrade. You can see there's some kind of evidence of regular distribution of ions with distance, but the strong one is the immediate neighbor, the nearest neighbor. This is at 4 degrees, at 25 degrees, and you can see that it's still there at 25 degrees. At 50 degrees, it's quite changed. The peak, the first peak is still about the same, but this part has changed considerably. At 75, it's almost straight here. There's still a peak. It's a little bit broader here than it was here. And at boiling, it was under pressure, so it didn't actually boil. There's another kind of a distribution and a much broader peak. Well, these studies led to mixture theories. This was the first really significant advance in the theories in that long period, almost 50 years. Since Morgan and Warren came up with a tritomite-free water mixture theory, there have been a number of mixture theories, and probably the most notable one is Pauling's mixture theory, which came out about 1960, if I remember correctly. Linus Pauling is a twice Nobel Prize winner. He was at Caltech for a long time. Interesting person. And he's now at an institute at Stanford. He came up with the clathrate theory. Clathrates are cage-like molecules. They're most noted in gas pipelines, natural gas pipelines, where if there's a little bit of moisture in the pipeline, these cage-like water clusters form around methane molecules and clog up the system. They clog up valves and they cause significant problems. So they try to keep methane pipelines dry. Well, chlorine hydrate also forms what are called clathrates. They're cages. They look very much, if you plotted the bonds, they look like the seams on a rugby ball or on a soccer ball. And he proposed that the water is a mixture of these clathrates and free water molecules, including free water molecules inside the cages. Those are probably the two most prominent mixture theories. Then about 1970, I'm not sure just the exact date of the paper, there was proposed, I've forgotten the authors, proposed flickering clusters. Theory. And the idea there was that the hydrogen bonds weren't permanent, but when one was made, it stimulated the formation of the next one and the next one, so that there were these clusters that would form and disappear and form and disappear. And I'll come back to that in just a few minutes. Then, lastly, about 1980, there was the gel with relaxing bonds theory. That is, that water's really a big gel, but the bonds make and break so frequently that it can flow. Now, let me go back and say some things about this mixture theories. Morgan and Warren pointed out a second factor that may be more important than their initiation of the theories. They said that the water molecule is determined from X-ray diffraction measurements on hydrates or solids containing water. Has a diameter of about 2.8 angstroms, 2.76 to 2.8 angstroms. And if you calculate the volume of water molecules in a mole of water, 18 grams of water, and the volume of the water, you'll find that the molecules only occupy 38% of the volume. The rest is empty space. That's probably the single most convincing bit of evidence that there's structure in water. The fact that the water molecules must be held apart in some way that keeps them in this open arrangement. Just for comparison, hydrogen peroxide H2O2 is about 59% molecule. When you combine that observation with the fact that water is very incompressible, it takes 200 atmospheres to compress water 1%, it's pretty evident that there's some kind of bonds holding the molecules apart from one another. Well, one of the criteria for any structure that we have is that the density has to be 1 or thereabouts at 4 degrees centigrade. You know, its density is about 1, and it really doesn't change all that much. Then there's been another group of investigators that have been concerned about thermal anomalies. And I must say, of all the controversial aspects of water structure studies, this is the most controversial. And the reason is that people have observed phenomena and then other people have not been able to reproduce it sometimes. But there's some that you can reproduce easily. The first one is the minimum volume at 4 degrees centigrade. You know, everybody agrees on that. The second one is that a lot of properties seem to change between 30 and 35 degrees, and particularly the specific heat. C, so at constant pressure, goes through a minimum. It's about 1 calorie per gram per degree centigrade, right? But it actually goes through a minimum. This is temperature, and this is specific heat. It goes through a minimum, but someplace between 30 and 35 degrees, about 33 degrees. If you subtract out about 0.9 something, 0.96, and then plot that, you'll see it goes through a very definite minimum. The viscosity of water, when the water is subjected to pressure, actually decreases with increasing pressure. The only substance that's known to do that. If you plot viscosity here against pressure this way, it goes through a decrease like this, then an increase. Say this is 4 degrees. And at higher temperatures, the change is a little bit less. And at 30 degrees, it's about gone. So below 30 degrees, there's some kind of structure that allows the viscosity to decrease with increasing pressure, at least up to some value of pressure. Really curious thing. Other thermal anomalies are the solubilities, products that change with temperature, the rates of reaction that go through what are referred to as kinks. If you plot the rate of reaction on a semi-log plot, there'll be a bend in the curve. It'll be a straight line against 1 over t, but there'll be a bend in it at 30 degrees. Other anomalies have been observed at somewhere around 12 to 15 degrees, 30 to 35 degrees, 65 about degrees, and possibly at higher temperatures. There's been 1 or 2 reported at 45 degrees. Well, these thermal anomalies are referred to as kinks by the skeptics and referred to as some kind of a transition by the believers. And I think the basic problem is that water changes with age, that the polymers, whatever the structure is, grows with time. And some people have used freshly distilled water, and some people have used old water, and you see more in old water than you do in freshly distilled water. I'll show you some of that in a few minutes. Well, the way it stands now, there are believers in the gel theory with high... Oh, I forgot something. The reason that the gel theory is around and the flickering cluster theory is around is that water has a very unusually high dielectric constant. That is, the molecules appear to be able to rotate up to a very high frequency. So they feel that, well, the bonds may... If they can rotate, then it must be able to break some bonds. But actually, the rotation can just involve the movement of a hydrogen atom from one molecule to the next, jumping across the bond. And that will give it an apparent rotation of the molecule. So I don't hold much with that. Secondly, why would a bond change its character as water melts, as ice melts, I mean, to water? Why would it change from a bond that's not relaxing in ice to a bond that's relaxing in water? No, this relaxation theory doesn't hold much water. So I don't subscribe to that. Well, you can see the state of knowledge. It's not very firm. We know there's some kind of structure in water. We don't know much about what the structure is like. We do know, though, that from plots like that radial distribution function and from the fact that the specific heat is high. Oh, I forgot one thing I should have mentioned. About 1930, Rodebush said that water must have some kind of structure, some kind of extensive bonding, because its melting temperature is so high and its boiling temperature is so high. He said hydrogen sulfide, remember sulfur occurs right under oxygen on the periodic table, hydrogen sulfide should be very similar to water, but it boils at minus 70 degrees centigrade. You know, and water boils at 100 degrees centigrade. The difference must be due to the fact that the water molecules are bonded to one another. That's an important point. Then, many people have said since that the exceptional heat capacity of water must be due to the fact that the bonds melt. That is, that as you raise the temperature, there must be more and more bonds that melt. You follow me? It's like the melting of ice. It takes a lot of heat to melt ice. 1.44 kilocalories per mole to melt it. Well, perhaps water from 0 degrees to 100 degrees, as you raise the temperature more and more, its heat capacity is due to the fact that you not only have to increase the motion of the molecules, but you have to also melt bonds. You have to break more and more bonds. And these radial distribution functions tend to bear that out. The peaks get broader, and the fluctuations away from the nearest molecule become less and less pronounced. Infrared measurements. Water absorbs strongly over virtually all infrared frequencies or wavelengths. And in order to observe anything in the infrared, you have to use a thin sheet of water. The studies that have been done so far show that about 91% of the bonds in water exist at melting at 0 degrees centigrade. So that further supports it. And then as the temperature increases, there are fewer and fewer bonds, supporting this view that the heat capacity is due to the melting of bonds. Well, that's a summary of the status of the molecular structure of water. Now, there have been a lot of studies I'll talk about in a minute having to do with water at interfaces, and I passed out at clay interfaces in particular. I passed out 2 articles that pretty well summarize where we are today. And they aren't new articles; they're not much further along, actually. And as you can see by the dates up there, we haven't made rapid progress. And the reason is that we don't understand the liquid state very well at all. Now what I'm going to tell you is some work that's been going on for a long time, but it's only part of it's been published. So we're getting off into the deep end now in water structure. But I think it will help clarify what happens in sediments as gelling progresses. Well, one thing we know is that we have to satisfy the density being equal to 1 in describing the structure. But we have something else to satisfy that I haven't mentioned so far, and that is the fact that it's a Newtonian liquid. Remember, in a Newtonian if you plot a velocity gradient against the shear stress, that in a Newtonian liquid, the shear stress at low velocity stress approaches zero, and the slope we call the viscosity eta. And Newton's hypothesis is pretty well observed, that the shear stress is equal to eta times the u dz. There's no shear strength. Now we have a material which on melting has 91% of its bonds made, and yet there's no shear strength to it. And this is the conundrum that's really caused difficulty in developing theories of the structure of water. And it's the reason that they go in for things like relaxing bonds, flickering clusters, and mixture theories to account somehow for the fact that the water is a Newtonian liquid, that it can flow without having any resistance, static resistance to flow. It has no shear strength whatever, zero. There have been very, very careful measurements made to try to find a static shear strength, and all of them show no static shear strength. So we have to somehow satisfy that as well in describing it. Pauling's clathrate model is kind of interesting because you can visualize these cages rolling along as big snowballs, so to speak. But in chlorine hydrates and methane clathrates or hydrates, they block up valves and things. They aren't really very, very useful. About, some years back, I embarked on a study to try to find some better description of water molecules, and I'm going to show you what I've concluded. But I want you to understand that this is not generally accepted yet, anyway. So with that proviso, I'll go ahead. The problems with X-ray diffraction measurements and neutron diffraction measurements is that they show that there's not long-range order, but the problem is that they can't distinguish what happens over any scale more than a few molecules, more than a few molecular distances from any one molecule. And I must say that studies using X-ray diffraction and neutron diffraction have really been exhaustive. There have been really extensive studies made, and the data that I showed you is about the best you can get from it. So I embarked on looking at another aspect, and I'm not the first to look at this aspect, and that is the viscosity of water. Viscosity is a mechanical property of the water that involves somehow the movement of one molecule relative to others. And it's a property that's very sensitive to the molecular structure of any liquid. A small change, even a change in an isomer, one isomer to another, changes the viscosity of the material. So it looked like something that could be investigated profitably. The problem I had was that there weren't any good theories of viscosity that could be used. There are another reason that I looked at viscosity is that it changes remarkably with temperature. In fact, the viscosity of water at boiling is 1/6 the viscosity at melting. That's a large change in any property. Theories of viscosity, I won't list them all. Probably the most known one is the Arrhenius theory. And he said that viscosity is equal to a constant times E to the constant B over T, where these are empirical constants to be determined. Then Eyring and his co-workers came up with they said, well, this B over T is really something else, and I'll just leave this in parenthesis, times E to the E over RT, or e to the energy of the individual 1 over kT, where this E he called an activation energy, and you'll see this term. And he said that the process involved the jumping of a molecule into a hole in a fluid. That first there had to be a hole made, then a molecule jumped. And he said there were parallel, during shearing, parallel layers of molecules, and that when there was a hole made, this molecule could jump into that hole, leaving another hole, but that it took this amount of energy for it to do that. That's his view. He wasn't talking about water, he was just talking about viscosity of liquids in general. And you probably hear about a number of Eyring's theories, particularly with regard to reaction rates, chemical reaction rates. But he says that there's some kind of a hill that this has to go over in order for the process to continue, and the rate that it goes over is dependent on the ratio of the energy, thermal energy of the molecule relative to the average thermal energy of the molecules. So he said that this is equal, and then he has a lot of arguments about what goes in here. And in fact, he's come out with several different things. We'll talk about that in a minute. Well, these are not very satisfactory theories, because the arguments about what goes in here are too vague. There's no way that you can apply them directly to a study of water. Well, about 1984, I think it was, I published a paper on viscosity of liquids, not including water, Newtonian liquids though. And it was based on this kind of an idea, and I'll just briefly describe it, that a liquid is moving with some velocity u1 relative, a layer, not liquid, relative to other layers at some viscosity u2. And that the spacing here is delta, and that each of the molecules, well, first of all, the layers may only form during shearing. That is, shearing creates the layers sliding past each other, or they may be permanent fixtures, but primarily formed during shearing. And virtually all of the theories on viscosity pose this situation, so that they're moving relative to each other, and that each atom or molecule in this in the liquid is undergoing thermal motion, so that periodically it moves up and interacts with I'll put it dotted, interacts with a molecule in the adjacent layer. And that interaction may be like a billiard ball colliding with the other one, or it may actually include an attraction. But its position changes in the liquid so that it interacts with a molecule on the adjacent sheet. And of course that's true for all of the molecules in either sheet. The molecule in the sheet is attracted to its neighbors, however, so that it has to include the mass of the neighbors in this momentum transport calculation. And the limit of the neighbors is determined by molecules who have enough thermal energy to break bonds and maybe initiate a nearby molecule. So that there may be a break here and say a break here, and all these molecules, the mass of all these molecules contribute to the exchange in momentum. Well, I won't lead you through the whole computation, but it leads to a description of viscosity that's equals to a constant times. Just a second, I'll put these down. Where alpha is the fraction of the thermal motions of any one molecule that result in an interaction with the adjacent sheet. This you have to find empirically. N is the number of atoms per square centimeter or per unit area in the sheet. Delta is the spacing of the sheets. M is the molecular weight of the atoms. M over N is the weight of the individual one. K is Boltzmann's constant, and H is Planck's constant. Planck's constant. So all these, the number per unit area changes very little with temperature, and the spacing changes very little. That's just the expansion coefficient, if you like. So we can lump these together as a constant. In fact, we can include alpha in that constant, and then say the constant effect changes with the fraction of interactions with the adjacent sheet. T0 for a number of liquids was found to be 0 up to a high temperature. What T0 is it's like a Dubai temperature. Any of you are familiar with that? When the thermal motions of the molecules are sufficiently great that their interaction with an adjacent molecule drives it into the next sheet, then you have a momentum transport that's accelerated, that's enhanced. This T0 is the temperature at which that begins to happen. For all the molecular liquids studied, there was hydrocarbons, which are long, flexible molecule, benzene and naphtha, which are rigid cyclic molecules, several isomers of hydrocarbons, alcohol, which is an associated liquid, mercury. Well, mercury is an atomic liquid, but except for mercury, all of these T0 was 0 from the melting temperature up to quite high temperature. So we'll take that for water. And if we lump all these in parentheses into a constant, we can write eta is equal to some constant B, which we can calculate actually from data, times the absolute temperature times E to the E over RT, which doesn't look all that much different from the Arrhenius relation I had earlier, except that now we know what goes in B, and we have this T in here. Some of Eyring's relations have a T in there as well, so that's not really all that new either. Well, this paper came out in Chemical Engineering Communications, and it describes the fit of this relation to this variety of molecules, and it describes the change in E with pressure and alpha with pressure and different kinds of minerals. The most important point is it fit all these things very, very precisely. In fact, it fit it as well as the measurements would allow. You know, they're always within the last significant figure of the viscosity relations over quite wide temperature ranges. Well, I don't want to dwell on this too much except to point out that it seems to be a pretty reliable description of Newtonian viscosities. Well, if we look at water, we find that it doesn't fit. And well, one of them didn't get copied.
There's one that's stuck to the first. The first one you showed us has a second transparency stuck to it.
Oh, did I have two on there? There it is. Thanks. This is a plot of viscosity of water divided by T. So that we have eta over T is equal to B E to the E over RT, or log of eta over T is equal to E over RT, 1 over T, I'll put it this way, plus. Okay, so we ought to be able to plot log of eta over T against 1 over T and have a straight line, right? And that's true for all those liquids I described earlier. But the data for water, measured every 5 degrees by Bingham and White in 1910 or 12 at the National Bureau of Standards, instead it falls off from a straight line. This is just a straight line drawn through it to show that it doesn't fit a straight line. All those others fit a straight line precisely. So something's happening to water. This is the lowest temperature, 0.26 degrees centigrade. The highest was just below 97 degrees centigrade. And you can expand the scale, of course, and get a much wider deviation. But the point is that it doesn't fit that straight line. And the reason is that the water is melting the structure is melting, as I described earlier. So we're dealing with a different fluid as the temperature increases, a fluid with a different structure as the temperature increases. If you look more carefully at these relations, at these data, you can discern that there's more information in there than appears here. And the approach taken was to take the difference to calculate, you can calculate B, you can write log eta 1 over T1 is equal to E and B, and log eta 2 over T2 is equal to E over R times 1 over T2 plus log B. So looking at each pair of points, each adjacent point, you can solve these simultaneously, assuming that E and B constant in that short interval, and find B and E, right? So we can calculate B and E for this relationship as a function of temperature. And when you do that, a curious thing appears. This is a part of that same data plotted on an expanded plot. And this, looking at E, now the bond energy, calories per mole, against BT. Oh, I forgot something. According to this model here, as more and more of the bonds are broken with increasing temperature, you'd expect the molecules to be freer to interact. So that alpha then should increase as E decreases. You follow me? So if we plot BT, the pre-exponential term here, against the bond energy, then you'd expect it to decrease. And the curious thing is that it decreases in a lot of short line segments. I didn't plot them all, but I plotted a few just to illustrate it. If you'll notice, the temperatures don't necessarily follow any particular order, but the relation seems to hold. The bond energy is mainly related to BT over short temperature intervals. And there's another one. These aren't the same. That is, it seems to break up into segments. Now this is from Bingham and White and Twining, done in 1911, I think, in 1914, at the National Bureau of Standards. It was very carefully done. It was done with water that was prepared and then kept for a long time. Two Indian workers, Qureshi and Ashinola, did the same thing. Oh, that's the wrong plot. Excuse me. I got them all mixed up here. Did the same thing, except they measured it at increasing temperatures and then decreasing temperatures. And their data show the same thing, that over very short ranges, that's ranges from 32.9 to 28.1, so about 3 degrees centigrade, seems to fit a straight line. Then over another range it seems to fit another straight line, and so on, up on through the thing. Pretty hard to argue that those don't fit short line segments. Now the root means computation supports that it gives fairly close fits to each of those segments. That's a curious kind of a relation. And I might say that we can write each of these for the short section as some energy. The energy we measure there is equal to a constant I'll call E0 minus nu bt, where nu is the slope of this line, and E0 is the intercept somewhere. You all recognize this kind of relation? You probably learned it in chemistry, in physical chemistry, as delta F, or F, you can write it, is equal to H minus T delta S. Remember that? Or TS? I don't see any great lights shining in here. that this is the free energy. This is the, do I have it right? The enthalpy, and this is the loss due to the entropy.
There's a delta in there, so
Well, I can put deltas in all these. That would make you happier. So that this E0 must be the enthalpy, that is the energy of the bonds that aren't broken. And this T delta S must be the energy of the bonds that are broken in the process or broken in the system. So we have a way of getting E0 out of these data. But they only apply for a very short range of temperature. Now, according to this model that we have up here, that means that the model must hold over a short range of temperatures, and then the structure must make some kind of a change, right?
when they collected these data, did they go all the way, I see something like 20.9 to 53.6, kind of in a series?
They
or
don't,
did go up
they,
and down and
they
so
don't,
on?
they don't say except that they went up. They said well, I take it back. The first data I showed you, they don't say. I just suppose that they increased the temperature. The way they describe it is they increased it, but they don't say they necessarily did it all in the same order. The second and third one, they definitely described an increase in stepwise. The third one I'll show you is much more orderly than this. But now we have two different investigators' data looks the same way. And then the third one, well, I'm not sure which is which now. Here's another one. Oh, this is a super cooled water. And you can see that they don't necessarily fall in order, but they still seem to fit a straight line at temperatures below freezing. Another reason that water structure is, another aspect of water structure I should have pointed out earlier is that it must be different from that of ice. It can't be icebergs in loose molecules, because you can supercool it easily to 20 below zero. If there were any ice in there at all, it would freeze altogether. And you can cool it to down to minus 40 degrees centigrade. So it must be stable, or metastable if you like, and different from that of ice. The structure must be different from that of ice. Now there are about 9 different ice structures, so it must be different from all 9 of them, right? Well, I don't have the third investigator's plots here, but they look the same way. There are segments, they're short segments that indicate that the water structure must shift in some way every few degrees. It doesn't necessarily melt continuously, but there must be some kind of shift. Now, the first investigator used old water. The second investigator used old water, not too old, but fairly old, and their data fit together very nicely. The third investigator, Professor Drost Hansen at the University of Florida, University of Miami, he's one of the kink people, one of the people that was looking at thermal anomalies. In fact, he's probably the most persistent of all the people that looked at thermal anomalies. He had a graduate student who made very precise measurements of viscosity at 1 degree centigrade intervals, and he measured the temperature to the 10,000th of a degree using a quartz crystal thermometer, and he used a capillary viscometer like the one I described to you with optical meniscus sensors at the scribe, so they can measure the time that it took to move the water through the viscometer 2,000th of a second. So he had 6 significant figures in both the temperature and time measurements. So he measured them precisely, and he measured them at precisely 1 degree differences within a 10,000th of a degree or 1,000th of a degree, at 1 degree interval differences, and he measured them repeatedly. And he kindly sent me Xerox copies of his notebooks. You know, he did measure them very precisely. And his data show the same kinks, but the range of temperature, the same straight line segments, but the range of temperature over which a straight line existed was much shorter than the other two. His student prepared newly condensed water for every day's measurement. At the beginning of the day, he condensed some water through triple distillation process and made his measurements, and then threw the water out and cleaned the viscometer. So his measurements were all made with new water, and the other measurements were made with old water. The Indian investigators increased the temperature up to 73 degrees, I think it was. Then they made measurements at decreasing temperatures. And what they found was that during the increasing temperature, the data looked just like the data from the other investigators, from the earlier ones. But the decreasing temperature, it showed shorter segments, and then this newly condensed water that I described also showed short segments. So you can conclude from that it's very likely that the difference in the length of segments is due to the size of the polymers. You know, after all, small polymers would change more easily than large ones. So that the water must take some time, on the order of hours or days, to grow to full size. Well, with that, with those data, you can calculate the fraction of bonds. Now, you might argue that what you're measuring is the result of a whole lot of bonds breaking and a whole lot of these processes going on in the system. After all, it's a bulk measurement of the fluid. And you're saying that the energy that you measure is proportional to the number of bonds that are broken or in the system. It really says it's proportional to the average over a large number of bonds. Now, the water molecules are already spaced pretty far apart. Remember, we said they had a very open structure. So that if they're very far apart, the bonds can be regarded as broken in an individual case. So you can say they're made or broken. There's some aesthetic problem there, you know, because actually the bond is just the force of attraction between two molecules. And if you pull them farther apart, there still must be some attraction. But saying they're broken and not broken is a certainly simplifying argument. John?
Back one step, when you talked about when you are in the heating mode, you have longer segments than the decreasing mode. So at higher temperatures, you've broken
It up.
Does that would that also pertain to higher velocity gradients?
It could, yeah. In fact, this last investigator that I mentioned that redistilled water every day also pushed his water through a millipore filter before using it, which provides very high velocity gradients, and that could certainly be a factor. Well, so if we say that this E0 is a measure of the number of bonds made, that gives us some clue as to what the structure looks like. And we have alpha back here that is related to the number of the fraction of thermal motions that result in an interaction. So we have some basis for interpreting these data. Now, if we take the center or take the average temperature of each of those little segments and plot this E0 against the segment average temperature. Remember, each segment was over a short range from which we determined E0. What we find is that at low temperatures, here's one we need more points in there to find out what happens there. But notice that these are from all three investigators now, all three sets of data, that they seem to fit a straight line here over a short range. Then we have another group that appear to fit a straight line. We might extend that a little further. And then this group appears to fit a straight line. And the real strong point is that these circles that you see in here are the ones that were most precisely made, that I described Professor Drost Hansen making. And you can see that they seem to fit a straight line pretty well. So I'm back to the kinks, if you like. There seems to be a change here at around 12 degrees centigrade, and another change around 30 in here somewhere, and possibly one up around 66 degrees centigrade. That's E0, and we can look at this nu, which is a nu B is the entropy, right? So nu has the dimensions. Well, I forgot. I'll dig it out for you if you like. But from that you can get a time, 1 over t. And the time turns out to be shorter than any normal motion of a molecule. It's about 10 to the minus 15th seconds, which must be the interaction time between the two molecules. And that plot looks like this. Plotted that interaction time against segment average temperature. This is the intersection. This is times 10 to the 15th. And you can see that in the supercooled region, up to about -6, it seems there are 3 points there anyway. Then these points fit a straight line quite nicely from somewhere around 10 degrees up to about 30 degrees. Then the 3 diverge quite a bit, and this is the Korean Ashenola's cooling is the solid one. Heating is the one we want. Bingham, White and Twining, the square, that's all heating. Q&A's heating are the triangles. One fits there, and there's one up there somewhere. And then their cooling one, which was immediately after it had been heated, falls on another group, and the Drost Hansen and Corson was the name of the student, fits in between there. But up to here it appears it's the same, and there seems to be a change somewhere around 30 and around 10 degrees too. Well, you can argue about what these mean. The approach I took was to say, well, what kind of a structure could do that? What kind of a structure would lead to all these things? And remember, we have to satisfy the density, and it has to satisfy the changes in E0, and it has to be a Newtonian liquid. It has to be free to shear. See, I forgot something along the way there. Oh, these plots indicate that remember, there were those short segments with the changes in E0 along the way, and they expand over quite a range of temperatures, fitting this simple straight line. The interpretation of that is that there's a transition from one structure to another in part of the liquid, and then another transition in another part. So I'm back to the mixture theory, if you like, over this range of temperatures. But then the mixtures, it's changes in short stages as the temperature rises. But at the end of this, it's all the resulting structure. Then that structure begins to break down to another one over this temperature range. And it's all the second structure. And then that begins to break down to another structure. So we have to somehow satisfy this kind of a decomposition process from one structure to another. And it has to meet all those other criteria, that it's a Newtonian liquid and that it's has a density of 1. Well, one structure that would do that is a 2-layer structure composed of rings, hexagonal rings, with bonds between the rings. And these lines indicate the bonds, and the junction is the center of the water molecule at each one. And this just shows a fragment of it. That it would be a 2-layer sheet, and using ice dimensions, 2.76 angstroms, to reach this density of 1, this has to be 3.26 angstroms to the top of the next sheet. Now, remember, parallel planes of atoms have stronger van der Waals attractions than do individual atoms. And it turns out that hydrogen bonds are pretty strong up to about 3 angstroms. It's shown by a lot of work for a lot of different hydrogen bonds. And above 3 angstroms, it's not very effective. So this is long enough so that it's unlikely that there are hydrogen bonds between the layers, but each layer would be distinct from the other. This is proposed as a structure below 10 degrees or 12 degrees centigrade, 2-layer sheets. Now the motion of molecules in these sheets, because each molecule is suspended by symmetrical 3-position molecules, the thermal motion would be dominantly out-of-plane motions in this arrangement. I made a model of it suspended on rubber bands and shook it and watched to see the thermal motion. And that's true. There tend to be out-of-plane motions. And as the out-of-plane motions increase, these layers can shift so that one layer has the molecule in the adjacent layer opposite a hole in its adjacent layer, so it has more room to vibrate. And similarly, this one is opposite a hole in the adjacent layer. When this happens, you have 0.875 in the number of bonds. I'll show you that in just a minute. And this persists up to 33 degrees about. Then, with further out-of-plane motions, you'd expect the sheets to come apart. And that's proposed from above 30 degrees to about 60 degrees, 66 degrees. And those sheets, these would be sheets, these are fragments of the sheets, would slide by each other, each one in enough thermal motion so that they can't produce permanent bonds. And they may actually face each other this way so that the bonds, there are some bonds between these sheets and then one between adjacent ones. Then at a still higher temperature, you'd expect the sheets to break down into chains of rings. And at boiling, they probably are ring fragments or a couple of rings. The first reaction you might have to this, well, first of all, this provides Newtonian liquid. You know, these would slide past each other without any trouble. First reaction you might have is, well, what about those bond angles? Kell in 1976, I think it was, George Kell, responded to Popel's paper in 1930, I think, 30-something. And Popel had an idea. He said that ice, when it melts, doesn't break a lot of bonds. The bonds may still be there, but the bonds bend to form some new kind of a structure. So Kell took energy necessary for a hedral angle to these angles, these particular angles, and he came out with 1.5 kilocalories per mole, and the actual value is 1.44. So these things are observed in the various ices, other ices, and in a number of other compounds. The best one is fluoroglucinol dihydrate, a benzene ring with one OH group on the end of it. So that bond angle is certainly a reasonable bond angle. Then I should Well, I had a... Well, I don't seem to be able to put my finger on it right a minute. But if you calculate the fraction of bonds made, well, first of all, E0 for the lowest temperature is, when they're all bonded, 6690 calories per mole. And if you calculate these and take that fraction of 6690 calories per mole, then it agrees quite closely with the observed values for the other temperatures. And the breaks take place at the temperatures that the data show. So it supports this kind of a structure. That is, it supports these numbers of bonds made in any case. Well, the hypothesis then is that we have planar polymers whose size may grow with time and that can slide over one another. I looked long and hard for some way to substantiate this kind of an observation, and one of the few things I found was an experiment by Professor Peschel in Germany, who took Peschel and Adfinger, took a polished granite plate, a polished plate, and then they polished a sphere, had a radius of plate that had a spherical surface, radius 1 meter, so it was very small curvature, and supported the second one on an electric balance, so they could measure very precisely the forces between the two plates. And they placed one plate in the bottom of a beaker, filled it with water, and put the other plate right next to it, and then measured the force necessary to pull the plates apart. And what they found was, they call that separation force. What they found was that if you plotted the force against temperature here, that it took more force at some temperatures than at other temperatures. Curious kind of a thing. Remember, these are plates being pulled apart like this, and that separation force seemed to increase. They also found that the viscosity increased very sharply as the plates got closer to one another. Well, even though these plates are polished, they're rough on a molecular scale. You know, you can imagine them as being rough on a molecular scale. But these distances, this is, I've forgotten. This distance was much greater than any roughness on the surface. And Professor Peschel wrote me and said that he doesn't know about this one. He's quite sure that this might be affected by the roughness of the surface, but he's confident that this one isn't. The temperatures, about 12 degrees, about 33 degrees, and this one's about 50 degrees, and this one's about 66 degrees. Temperatures coincide, except for this one, and some of these other data show that one, coincide with those temperatures at the ends of those transition zones when you would expect all of fluid to have the same structure. So when it all has the same structure, it's stronger, takes more force to pull it apart than when it's breaking up by thermal motions, which seems to support this idea of a gradual transition from one structure to another. Now, these structures might not be the right structures, but they have the right number of bonds. Then they do provide Newtonian flow, while at the same time allowing virtually all the bonds to be made. The problem, I'll remind you, the problem is that we have to have a liquid that has 90% of the molecules bonded to each other, 91%, and it has to be able to shear. This meets those conditions. Now, what I'll show you on Thursday is how this leads to gelling sediment. Then we can get on with the sediment bed. So today's been a kind of a digression, if you like. If you're interested in properties of water, there's a huge literature out there, and I encourage you to look into it. Start with the latest and go back, though, because there's a lot of dead ends. One is polywater. Have you all heard of polywater? In the 60s and early 70s, Derjagin in Russia described water in capillaries that formed in capillaries. You could condense water in capillaries, and this water had an unusually high viscosity. And he said it was some kind of a polymer, and they called it polywater. They coined that word for that thing. Derjagin is a very respected researcher, and so everybody jumped on the bandwagon, and people were making polywater all over the world. And the papers appeared, you know, again and again. It was discovered later that polywater was due to the fact that you were including some of the glass in the water, and that what you had was a sodium silicate kind of problem. And so polywater became a word in disrepute. And the kinks, the matter of kinks, some of which I've shown you here, have had papers written that were very, very skeptical. George Kell, who was at the National Research Council for Canada, very good man, and Falk wrote a paper saying the kinks aren't real. You know, pretty persuasive kind of a paper. You'll find that all through the literature. It's interesting from its human side. Well, we don't know much about liquids. You'll find on Thursday that there have been a lot of measurements on liquids near interfaces, and there's a lot of discussion about that too, but I think there's more agreement there than there is in the case of what the structure of the liquid is. Well, enough for today. I didn't pass out to you homework number 3, which I'll leave it.
No, I got your next one.
Oh, thanks.
Would you all take a look at your calendars between now and Thursday, and let's plan a field trip. Look at your calendars between now and Thursday, and let's plan a field trip on a Saturday. So if you look at your next several Saturdays and see which ones are available, and then let's plan them. It'll be pretty much all day. We'll go down around the bay area.